Our last video of the semester is going to be on equivalence classes. First thing we're going to do is review the definition of equivalence relations, which is where equivalence classes come from. Next, we're going to use the family model of equivalence relations to help us understand equivalence classes. We're going to actually find equivalence classes in an example equivalence relation. And then we're going to look at the connection between equivalence classes and something called a partition of a set. So just review some definitions. If A is a set and R is a relation on the set A, we say that R is reflexive if every element of A is related to itself. We say R is symmetric if whenever A is related to B, then B is related to A. And then we say R is transitive if whenever A is related to B and B is related to C, then it follows that A is related to C. And if all three of these happen, all three of these properties are true, then we get what's called an equivalence relation. An equivalence relation is a relation that satisfies the reflexive property, the symmetric property, and the transitive property. All right, so another thing I want you to review is the family model for equivalence relations. And remember, in this one, we were thinking of an equivalence relation as a family relation. In other words, we say A is related to B is something like A is in the same family as B. And that's what gave rise to the three properties: reflexive, symmetric, and transitive. So I want to have two observations about this model with respect to equivalence relations. First of all, the fact that families exist, again, and these families are sets of people, give rise to the equivalence relation. So once we have the families, that helps us define what the equivalence relation is. The second is more of a question than an observation. If you have an equivalence relation, is it possible to reconstruct those families? So if you only know which pairs of people are related, can you somehow find those families knowing that you have an equivalence relation? So let's see. So let's try to think of a strategy of how we'd actually find families from a relation. So you can imagine a room full of people, and if you wanted to separate them into groups where each group was in the same family, how would you do that? Well, the one thing and this seems like an obvious observation, but every person is part of a family. So that means once you've chosen a person, you've chosen a person who's part of a given family. Now, once you choose some random person, what you can do now is figure out who their family is by finding all the people related to the person. So if you imagine this room of people, you pick a random person, you ask, hey, is there anybody in the room who's in the same family as this person? All the people in their family will come together, and then they'll group together as a family. So this leads us to a definition that's more related to equivalence relations, but think of it as that same process that we just described. So again, we're thinking of R as an equivalence relation on a set A, and we're going to let little a be an A. The equivalence class of little a is denoted by R of A, and is given by, well, it's going to be a set, and it's going to be R of A equals the set of all x, such that x is related to A. So let's see if we can deconstruct that and sort of figure out how that relates to what we were talking about before. So in the context of the family model, what's happening? Well, the element A is like the person we chose at random. The person we said, hey, this is a person who's in this person's family. Well, once we choose, and again, that person we know is part of a family. We may not know which family, but it's part of a family. The statement X is related to A is saying that X is literally related to A. So X and A are in the same family. So X is part of A's family. So this is like the part of the process where we're saying, hey, is anybody in A's family? And we gather all the people who say yes. And then if we think of what that makes R of A is literally the set of all people in A's family. So we take A, we gather up all the people in A's family by using the relation, is X related to A? And then that becomes an entire family. Which means that literally the set R of A is A's family. All right, so let's see how this works in a congruence relation. So this is a relation on numbers. And so here when we're talking about numbers who are in the same family, numbers are related to each other by a congruence relation. And the congruence relation we're going to use, let me see. So the relation R is defined as follows. We say X is related to Y when X is congruent to Y mod 4. So two numbers are related if when you subtract them, they are a multiple of 4. So the question is, what are some of the families? And so the family I want to find R of 3. And remember what that means. What I'm doing is I'm randomly choosing the integer 3, and I'm asking who is in 3's family. Which numbers are in the same family as 3? Well, the test of whether or not you're in the same family as 3 is using that congruence mod 4 relation. In other words, you want to find numbers x where x is congruent to 3 mod 4. So we can find a lot of family members this way. 3 is in its own family, of course, so that's going to be in there. 7 is in 3's family because 7 minus 3 is 4. That's a multiple of 4. 11 is also in the family, 15, 19, all those, right? You also get some negative numbers, right? 3 minus 4 is negative 1. That means negative 1 is in the family as well, and etc. So you get a whole bunch of numbers that are in 3's family. So in general, we're looking for all the numbers of the form x equals 3 plus 4n, where n is an integer. And if we want to put those in a list form, we have dots going off to either side, but we just sort of start negative 9, negative 5, negative 1, 3, 7, 11, 15, and then all the, keep adding multiples of 4 on either side to get all the numbers in that family. And another way we can write it, if we want to write it as in set builder form, so we can say they're all the elements of all x in the integers such that x is equal to 3 plus 4n, where n is an integer. All right, so that's one equivalence class. That's one family. How do we find a different one? Well, we're going to ask somebody else in the room who their family is. So I'm going to pick the number 7. 7 is different than 3. I already found 3's family. Let's see if I can find 7's family. Well, if I find 7's family, then I get, oh, wait a minute, negative 9, yes, because negative 9 and 7 are 16 away from each other. That's a multiple of 4. Negative 5, yeah, those are 12 away from each other, so that's a multiple of 4. Negative 1, those are 8 away. Then 3, 7, 11, 15. That should look a little familiar, maybe. That just happens to be exactly the same as R of 3. So that's a little bit disappointing. We thought we were choosing a different number, so maybe we'd get a different equivalence class. But it turns out we got the same equivalence class we got before. And the question is, how could we have known that at the beginning? Well, one thing to notice is that 3 and 7 are in the same family. So that's like asking, okay, let's find everybody in my family, and you gather all those people together, and then you say, okay, let's see who's in my brother's family. And of course you're going to get the same people because my brother and I have exactly the same family. So we just happen to choose two numbers in the same family, and so of course we're going to get the same equivalence class. So what we're going to have to do if we want to find a different equivalence class is find a number that's not in the family. And if you look carefully, 0 is not in the family, so that should give us a new equivalence class. So there we're going to get 0, we're going to get it 4, 8, all multiples of 4, right? Negative 4, negative 8, we're going to all multiples of 4, and notice that none of those is in the family that we had before. And notice that the number 1, positive 1, is in neither of the families that we've seen so far. And so we get these numbers, we get 1, 5, 9, etc. going in the positive direction, and then negative 3, negative 7, etc. going in the negative direction. And R of 2, we do the same thing. We take 2 and we add or subtract multiples of 4 to get various numbers. And then, I know we've already found R of 3, but I'm going to put that one in there too. And then the question is, okay, any more? And it turns out, no, there's not going to be any more because we've used up all the integers. For instance, if you start at 0 at that top row and sort of work down that column, we got 0, then right below it is 1, then below that is 2, below that is 3. And then if we move one column to the right, we see we get 4, 5, 6, and 7. Move one column to the right, we get 8, 9, 10, 11. And if we keep going to the right, we're going to get all the positive integers. If we play the same game with the negative numbers, we start at the bottom with negative 1 and work our way up. We get negative 1, negative 2, negative 3, negative 4. The next column over is going to be negative 5, negative 6, negative 7, negative 8. And then you can see you're going to get all the negative numbers as well. So if we run out of integers to put into a new equivalence class, that means we don't have any more equivalence classes. We just have those 4 equivalence classes. So that means that these four equivalence classes, R of 0, R of 1, R of 2, R of 3, those are all the equivalence classes of the congruence mod 4 relation. So now I want to sort of talk about a new concept called partitions. But before we define those, I'm going to make some observations about families. First of all, every person is part of a family. We mentioned that before. Every person is part of their own family, of course. And then the other thing is that no person can be part of two different families. And so what those properties are, if we sort of abstract them, is they make up the definition of what is called a partition of a set. All right, so let A be a set, and let A1, A2, etc. through AN be the subsets of A. Now, again, we're thinking of this as part of an equivalence class, right? So we're thinking of A1, A2, AN. Those are going to be the different families in that set. So we call these subsets a partition of A if both of the following are true. And each of these is going to go with a bullet point. So the first bullet point was every person is part of a family. And that means A is the union of all those A1, A2 through AN. And what that means is everybody in A is in one of those families. It's either an A1, or if it's not an A1, then it's an A2 maybe. If it's not an A1 or A2, it's an A3. But it's in one of those AIs between A1 and AN. And the second thing is that none of the different families have anybody in common, right? No person can be part of two families. That means if you take the intersection of two of those sets, two of those families, you get the empty set. And we got a couple theorems that we're either going to prove in class or you're going to prove on your homework assignment about the relationship between equivalence relations and partitions, because they both kind of act like families. The first is, if R is an equivalence relation on the set A, it's a family type relation, right? Then the equivalence classes of R form a partition of the set A. In other words, if we look at the equivalence classes, if we take the union, we get everything in the set A, which we did see in the congruence mod 4 relation. And also, if you take any two different equivalence classes and find their intersection, there are no elements in their intersection. Their intersection is empty. And here's another theorem you're going to be working on your homework that says the same thing kind of in reverse. If you happen to have a partition of A, so if you have these sets A1, A2 through AN, if those are your families, right, your subsets that form a partition of A, then that allows us to define the relation on the set A. And we're going to define it just like we did for families. We're going to say that X and Y are related precisely when X and Y are in the same family. They're in the same AI. If we do that, then it turns out that R, that relation R, is an equivalence relation on A. So what these two theorems together say is, first of all, if you have an equivalence class, that enables us to break up our set into a partition. And the second theorem says, if you have a partition of your set, then you automatically have an equivalence relation, and those subsets in the partition are the equivalence classes of that relation. All right, so now you're ready to work on the activities for, I think there's two sets of activities. One is called the equivalence class example, and the other has to do with the equivalence class theorems that you're going to be working on your homework and that we're going to be working on as a class.